Hello, hello engineers. Am I audible? I hope I'm audible. So today we have a session on common source amplifier, and now we are going to designing part. Okay. Till now we studied about, okay, we have a resistance, we have a load, we have a operating point, we have a quiescent point. How we can is bias? How can we use a different load, like we are using a resistive load, we are using a that is active load, current source load, okay, and CMOS inverter also. So we use different type of load. On the basis of that we design a common source amplifier. Today and tomorrow we will discuss how you can achieve the gain by that putting that value, because as per the analysis you are talking about the linear, but once you go for the designing of that part, that will be a non-linear. So how can you design? By the help of LTspice. So today we will design a circuit, a common source amplifier with a resistive load, and that will be given some design specification. And tomorrow we will design by the help of Cadence Virtuoso. So of course that LTspice is familiar to everyone, and it is open source, so you can design it. So let's start with a common source amplifier with have some design specification. So the design specification is this. I am giving very simple design specification so you can relate it. Let the power dissipation is 150 microwatt. Okay, and that on the basis of that, what will be the width? And width will be 10 micro, length is 1 micro, so that it have a less second order effect or a channel length modulation effect. If you have higher length, so of course it have a less effect. And that VDD is given is 5 volt. Okay, on the basis of that you will design the circuit. What will be the RD, what will be that, okay, and let it you assume it ki, okay, you are designing for that threshold voltage is 1 volt. So we have some specification. On the basis of that we will design it. Once you will design with the Cadence Virtuoso, on the basis of the technology node you will find it what is the VTH. By the help of LTspice we can define it what is the VTH of that MOSFET. Okay, so this is given to you. Let's start with a very basic thing. Okay, that circuit have a like this. This is a common source amplifier where that you have a RD, you have a VDD, that you are taking the output at the drain and you are giving the input at the gate, and the source is common for both. Okay, so where we know that the VDD is 5 volt and the given is power dissipation is 150 microwatt. So if the power dissipation is 150 microwatt, you can say that power dissipation is equal to VDD into ID, and that ID is what? That ID is equal to 150 microwatt upon VDD, that is 5. So this is 30 microampere. So we can say that for this type of power dissipation we require a 30 microampere current. Okay, so on the basis of that power dissipation we define that what is the current requirement of the circuit, and if you know the current you can define it what is the VGS, because ID is equal to half mu COX W by L VGS minus VTH ka whole square, and I am assuming at the lambda is 0, the channel length modulation is 0. Okay, the lambda is 0, and that MOSFET I am trying to make that MOSFET in saturation region. then only I can use this formula. And I am assuming that VDS is greater than VGS minus VTS. So what will be the VGS if I am thinking about it? What will be the VGS? Okay, so VGS is what? So VGS is equal to, if you are solving it, this is 2ID upon mu n COX W by L, and that will be under root plus VTH. Yes, everyone. So that what is VGS? That is 2ID upon mu n COX W by L, that will be under root, and that overall it will be plus of VTH. Okay, that is very, very important whenever you are solving it. Okay, of course we can analyze common source amplifier in terms of understanding. Okay, we have a resistance, we have a this, we have a this. Okay, let's try to design it. Okay, and we miss one part. Okay, that gain is also is given. So let the gain is, I am assuming that gain is 20 dB. The gain is 20 dB. You are designing that common source amplifier with have a power dissipation is here. W is given, length is given, VDD is given, threshold voltage is given, and you are designing for 20 dB. The gain would be 20 dB. So let's on the basis of that, I find that the starting point, that what is the power dissipation of the common source amplifier is 150 microwatt. On the basis of that, we can say that the current will be 30 microampere. If you are talking about the power dissipation is 150 microwatt. So current is 30 microampere. And if I am assuming that MOSFET is saturation, if the MOSFET in saturation, that let I am assuming it MOS in saturation. If MOSFET in saturation, that this is the equation, ID is equal to half mu n COX W by L VGS minus VTH ka whole square. On the basis of that, you can write it VGS is equal to under root 2 ID upon mu n COX W by L plus VTH. And if we are assuming that what is that VGS, that VGS is equal to under root 2 ID upon mu n COX W by L plus VTH. Okay, just solve this. Okay, we have a 2 ID is 30 micro, and mu n COX, I am assuming that Kn is equal to mu n COX, that is 50 micro. Okay, so if it is 50 micro, just put it here, that is 50 micro, and W by L is 10 by 1, that 10 micro by 1 micro, and this is plus VTH, and VTH is equal to 1 volt. So on the basis of that, what is VGS, you can calculate it. This is 60 micro upon 500 micro plus threshold voltage 1. So if you are solving it, I am taking that calculator, and by the help of calculator I am saying that okay, this is 60 by 500 and power 1 by 2 and plus 1. This is nearly equal to 1.346 volt. That VGS is 1.346. On the basis of that, you can define it. What is the VGS? I am just using a basic equation. Okay. So you have a two technology, that you can use that GM over ID method. Okay, and you can use this method also. You can design a common source amplifier by the GM over ID technique, or by the help of this common source amplifier by the basic equation. We have some design specification. On the basis of the design specification, we know that what is the drain current, and if you know the drain current, you can use this formula, or I can say that if you know, so you can use this. Otherwise, if you want an exact value of that VGS, just use a MOSFET here with the current source and make that MOSFET in a saturation region perfectly. And this is 30 microampere. If you are trying to solve by the help of tool, Of course, tool have a lot of variation. It have a gamma, it have a lambda, it have a that is channel length modulation, that is second order effect. Lot of parameters it have. In LTspice, you set that value, but in a cadence you have a lot of things. So in a cadence we will solve in such a way that okay, you have a 30 microampere. On the basis of that, you put it W is equal to 10 micro and length is 1 micro. So you can find it what is the VGS here. For what value of that VGS? For this W by L, what is the current is 30 micro. And if I am assuming that is length is higher, so I am assuming that VDS is not affected of the ID, that will be approximately slope is 0. Okay. Or you can use this method, that is VGS is equal to under root 2 ID upon mu n CXWI plus VTH, and like this. So this is given 1.346. I am saying the approximate value. Of course, it have a lot of parameter. So it is not perfectly like 1.346. It can be 1.35 or 1.37 or 1 point something. 1.34, 1.35, 1.36. That is okay. Is it? So if you want exact value, you can go for that tool. On the tool, you just design this circuit. Okay, you have a current source of 30 microampere. On the basis of that, you can decide what is the VGS, and that will be the exact value, because tool will decide it. So on the basis of W by L, if you have a current source, so what is that voltage? Okay. So we have a VGS here. Okay. And on the basis of that, you can define it VTH also. You can use a DC parameter, DC analysis. On the basis of that, you can calculate VGS, you can calculate VTH. Yes, is it? Okay, let's talk about that gain. So till now we decided that VGS is, by the calculation, is approximately 1.346 volt. I think so. This is like 1.346. Yes, correct. This is 1.346 volt. Okay. And now I am going for gain. The gain is what? That gain is 20 dB there. That is GM RD parallel of R0 by the help of common source amplifier. This is 20 dB. 20 log of this is a 20 dB. That common source amplifier, have a gain is what? The gain is AV is equal to minus GM RD parallel of R0. We discussed that part in last Saturday and Sunday. The gain is minus GM RD parallel of R0. If lambda is 0, so R0 is approximately infinite. So this is RD minus GM RD. So 20 log of this. So if you are cancel this 20 and 20 and you converting it, so this is GM RD parallel of R0 will be 10 times of 10 ki power of 1, because 20 is cancel out, and this log is base 10, so it become a 10 ki power 1. So GM is equal to, or I can say that if lambda is 0, so GM RD is equal to 10 there. Okay. So if GM RD is 10, so let's try to determine what is GM firstly, and then we will go for the RD. So GM is equal to that, you know ID, you know VGS, you know VTH. So you can use you have a 3 formula. On the basis of that, you can use it. This is VGS minus VTH there. 2 ID upon VGS minus VTH is one of that formula. You can use GM is equal to mu n CUXW by L VGS minus VTH. You can use GM is equal to under root 2 mu n CUXW by L into ID. As per understanding, as per the known value of that, you can use. You have a 3 formulas of the GM. Okay, we know ID, we know VGS, we know VTH, we can determine what is GM here. So GM is what? That is 2 into 30 microampere. VGS is 1.346, I think. What is that value? 346 minus VTH is 1 volt. I am assuming that VTH is 1 volt. So this is what that GM is what? That is approximately 60 micro upon 0.346. You can calculate it is what? 60 micro upon 0.346. 60 upon 0.346. That is 173.41 microsiemens. So this is your value of GM. The GM is 173.4641 microsiemens. Okay, so you have a GM value, you have a GM RD value. Just put it here and determine is what is RD. So that RD is equal to what? That is 10 upon something. What is that something? That is GM. That is 173.41 microsiemens. On the basis of that, you can decide it what is that RD. So this is 10 upon 173.41, and that in terms of RD in kilo ohm is what? That is 57.67 kilo ohm. Okay. So this is the value. Okay. So you find that all that value, here you have a GM, here you have a RD, and everything you have. You can check the MOSFET in saturation region is not. So what is that? How can you check that MOSFET in saturation? You know VDS is what? VDD minus ID RD. You know VDD, you know ID, you know RD. You can check it. What is VDS? What is Vout? If Vout is greater than VGS minus VTH, if it is greater than 0.346, I think what that value is 0.346, that will be higher. Okay, so check it. It's a MOSFET in saturation or not. So I am checking that. Okay, you have a value. What the value you have? Till now you have this circuit, and on the basis of that you decided that RD is 50. What that value? I don't know. At 57.67 kilo ohm. That is approximately 57.67 kilo ohm. And you have a voltage is 5 volt. This is, I am just assuming that the voltage is 1.346 and the current is 30 microampere. So what is the Vout? Vout is equal to VDD minus IDRD. That is a large signal model. So on the basis of that you can check it that this VDS is greater than VGS minus VTH or not. Okay. So VDD is 5, ID is 30 micro and RD is 57.67 kilo. Just multiply it and check it. This is VDS is greater than VGS minus VTH or not. So this is 30 micro into 57.67. That will be your, and into 1 into 10 ki power minus 3. This is 5 minus 1.73. This is 5 minus 1.73. Just 5 minus 1.73. This is nearly about 3.27. And that Vout is 3.27. So I can say that, okay, that's VDS is greater than equal to VGS minus VTH. VGS is 1.34 and VTH is 1. So this is 0.343 and VDS is very far away to VGS minus VTH. So that MOSFET is perfectly in saturation there. Okay. So this is that happening here. Okay, let you are trying to design a common source amplifier, you don't know what is RD and what is that current. By the help of power dissipation you can calculate it, and on the basis of that you can determine it what is the current. And if you know the current, what is the voltage here for this current, for the W by L is equal to 10 micro upon 1 micro. On the basis of that you will define it what is that voltage drop across RD, and that will be 1.73. The voltage drop is 1.73 if the current is current is 30 micro and RD is 57.67. Okay, so this will be the value that V out is VDD minus ID, that is VDS is very very far away to VGS minus VDS. I am very sure about it, the MOSFET in saturation region. Yes, you want that gain is AV is equal to 20 dB, or in magnitude you can write it 20 log of AV is equal to 20 dB. So AV is 10. You want that 10 or more than 10. Of course, that is, if anyone say that 20 dB means you are always trying to make a higher gain. So that gain in magnitude will be 10 or more than 10. So V out by V in must be greater than equal to 10 there. Yes, everyone. Is it okay? So till now we discuss all this part. Okay, you can put it and how can you solve it, and by the solving of that you can determine what is that value of W by L. On the basis of that you can determine what is that RD, what is that current, and what is that gate to source voltage, and of course it will be okay. So this is the way you can solve it. Let's try to make this logic on a LTspice with the given parameter. What that parameter, that I am assuming that mobility and mu and COX is Kn is equal to 50 micro and threshold is 1 volt, W is 10 micro and length is 1 micro. On the basis of that I am trying to find out what is that happening here. Okay, so let's try to design this logic on a LTspice. Okay, so I am going for LTspice window and I am trying to hit. So this is a LTspice window. In this LTspice, you know that this is a new schematic. You can use a new schematic, or I can say that you have a LTspice here. Just a minute. Yes. Okay, so this is a LTspice window and you have a schematic window of that. If you want NMOS, you justly go for that component. You can press P or you can go on that component. Just click on this and you have a NMOS. So you have a NMOS at here, and this is NMOS. I am taking a four terminals of NMOS. Just this is NMOS there. Escape. Okay, just placing of that MOSFET and just escape it. That mouse will release that symbol. You have a resistance. I am just making that a smaller one and zoom out. And just I am using a resistance here. This is a resistance. And you want a voltage here. And you want a voltage here. So this is VDD and this is your VGS. And I am just connecting the wire So this is wire connection. This is wire connection head here. Okay, this is wire connection here. And of course this is, I'm just making that this is floating. Once we will connect by the ground. Okay, and this, oh sorry. I want this wire to connect with the source. Body is connected to source. Why? Because VSB is 0. If VSB is 0, you will find that there is no effect of VTH. If VSB is not 0, it have a VTH will be affected with a VSB. Okay, so I don't want any effect on VSB, or I don't want as a threshold voltage. That's why I'm connecting source and body is sorted to each other, and I am connecting ground. So this is ground is connected here, this ground is connected here, and this ground is connected here. Okay, I can make the sort also, there is no problem. I am just connecting here. Okay, so this is that circuit. You know that what is that DC voltage? I am saying that VDD is 5 volt. You can put that value, or you can change that name also. If you are interested on that name changes, you go for VDD. This will be a VDD, and this is RD. If you want for better representation, you can go for this. This is RD, and what is that value? That value is what? That is 57.67. I am just writing 57.67 here, and that is kilo ohm there. Okay, so this is 57.67 kilo ohm, and the gate voltage what that I am providing, the gate voltage 1.346. This is 1.346 there, 1.364, and you can put that name here VGS, because that source is grounded. The gate voltage same as VGS here, so you can put it, the name is VGS, so you can better understand. So this is your VGS, and you have like this. So this is that circuit, and now I am trying to set that MOSFET, that internal parameter of that. So I am going for SPICE directive. In a SPICE directive, I am writing that model file, that dot model. Okay, NMOS space NMOS, and I am writing in such a way. Okay, you can change the name also if you want. You can put it NMOS 1 or NMOS 2, NMOS 3. You can change the name. If this is NMOS, and you can change the name, then NMOS 1, NMOS 2, NMOS 3 is per to you, or you can give that name is NMOS A, NMOS B as per your requirement. I am just giving VT 0 is equal to 1 volt, width is 10 micrometer, and length is 10 micrometer, and what is that Kp, that is mu n COXW, mu n COX, that is 50 micro. I assume it, so I am writing 50 micro here, and lambda LMBDA lambda is equal to 0. I am assuming lambda is 0, and gamma is, that is one of the factor. I am just assuming that gamma is 0. So just like lambda you have a parameter, just you have a gamma also. That in a fabrication terms, that you have a lot of parameter. Once that you are going for a solid state, in a solid state, that they just use a block by the help of silicon and germanium or anything. They are using a material, and they are trying to make a that is amplifier. Okay, so this is not only given ID is equal to half mu n COXW by L VGS minus VTH ka whole square. It is not like this. That when you go for a solid state or microfabrication technology, you will find that you have a lot of parameter beyond that. This is not only 1 plus lambda VDS, you have a 1 plus gamma and 1 plus something beta and something like this. So for our understanding, for a circuit designer, we are not going for that much amount of verification. I am just assuming this is okay, this is okay for me. Just like you have a binomial and you have 1 minus x ki power minus 1. So this is 1 plus x square upon 2 factorial plus x cube upon 3 factorial, just like this. And let x square is very, very small, x cube is very, very small, x to the power 4 is very, very, very small. So you just put it 1 plus x there. So just like this, you have a lot of parameter. We can avoid it, so we are just assuming it. Okay, that lambda, let that I am just assuming that this MOSFET is ideal. So lambda is 0, gamma is 0. Okay. So this is happening here, and I am providing that this is the model here. Okay. So you can change that name is NMOS1 or NMOS as per your understanding. Okay. There is no any requirement. If you want, you can place it NMOS1. If you place NMOS1, you can just change that NMOS1 here also. Okay. So this is happening on the basis of that. You set that operating point of that the threshold voltage, and you are setting that the value. You have a VT naught, you have a W, you have a length, you have a KP, you have a lambda, you have a gamma, you have everything on that. And on the basis of that, I will go for operating point. You have a lot of analysis. You have a transient analysis, you have a DC analysis, you have a AC analysis, you have a noise analysis, you have a operating point. So on the operating point, just like a cadence, you said that save the DC operating point. On the basis of the saved DC operating point, you will find that value of VGS, VDS, CGB, CBS, CBD, that lot of capacitance. Okay, on the basis of that, you have a DC parameters. Okay, so if you are providing the gate to source voltage and you are providing that and VDD, so you have some current. On the basis of that, what will be your voltage? What will be the MOSFET configuration? On the basis of the MOSFET configuration, how that MOSFET is work like this. So I am just saying that, okay, you have this, okay, that you have a gate to source voltage, you have a MOSFET, and you are setting like this. So just run it. So before the run, just go for operating point for the analysis. So you have a DC operating point. You can go for simulation and go for configure analysis, or you can press .ac. So you can press .ac and you have a DC operating point. So just by the DC operating point, you can OK. If you OK it, so it will be .op. So this will provide a value for that amount of gate to source voltage, for that amount of VDS, what is happening in the MOSFET. Okay, so it will explain everything in terms of VGS, VDS, ID, everything. Okay, so just I am not sweeping any gate to source voltage. I am not going for any type of sweep and any type of graph. I am just want for this particular value of the gate to source voltage, for this particular type of drain to source voltage, what is the MOSFET configuration, what amount of output, that what is the current, the MOSFET in saturation region or not. I want just only basic things. Okay, so I am here only for this. So I am just run it. After the save, just run it, and after that run, you will find this type of value. And I am just going for view and SPICE output log. In the SPICE output log, you have a it is not providing. Okay, this is happening here, and I am just copy it, Control C, and I am trying to place it here and check it. That is command text, and you have this type value. What I am doing, just repeat it. So I just put it VGS here. On the basis of that, I am put in W and L and the KP and lambda and gamma. Okay, and just I am trying to figure out what is that. Okay, length is 1 micro there, not in 2 micro, it is 1 micro. I am just, that's why that have a problem. Okay, so length is 1 micro there, length is 1 micro, this is like this, and W is 10 micro and length is 1 micro, everything is done. And now I am just going for DC operating point, and I just want that value. Just go for view and you have a SPICE output log. You go for a SPICE output log, you just click on this and press Control C for copy, and you can right click on that and you have a draft. In the draft you have a comment text. It's not any spice directory, it is text. So just place it here, Control V, and you can check it. This is the value there. I am just zooming here, okay, and you can change that value, that you can, okay. So you can check it. ID is to 29.9 micro. This is 10k power minus 5, and you want 10k power minus 6, so this will be 29.9 there. So this is 29.9, that will be a 30 micro. So that ID is 30 micro, and you have a VGS. On the basis of you have a VDS, we check it. What is the VDS? That is 3.27. That is approximately VDS is 3.27. So if VDS is 3.27 and VGS is 1.35 and VTH is 1 volt as we assume it, so that VDS is greater than VGS minus VTH, that MOSFET is perfectly in saturation region. And let's talk about transconductance, that GM. So GM is equal to 1.73 into 10k power minus 4. If you are calculating, this is 173. The GM is what? You can check it. What is the GM? I am just checking that. What is the GM value? So yes, that is 173.41 microsiemens. This is 1.73 into 10k power minus 4. So the transconductance is 173. Okay, microsiemens. So you have a transconductance, you have everything, and the GDS is 0 means lambda is 0. Well, I am just saying that GDS is 0 means that RDS is infinite, because you are assuming that lambda is 0 here. The slope is GDS. Why GDS? Because ID versus VDS graph you have. VDS is changing, ID is not changing. So dou ID by dou VDS is your GDS, and that is 0. Okay. So this is perfectly matching as per your calculation. So your calculation was current is 30 micro, that is okay. Your VGS is 1.35, that is okay. Your VDS is 3.27, that is very good. You assume it VTH is 1 volt, that is also present here. You find that GM, that is 1.73, yeah, 173 microsiemens, that is also present here. So everything is okay. Okay. So I am not going for changing the resistance value. I am just putting that okay, if you have a particular design specification, you can design your circuit. Okay. And let's talk about it. Okay, what will be happen when you are using a signal as AC signal? This is for quiescent point. This is for what? This is for operating. This is operating at that gate to source voltage, at that to drain to source voltage. Now I am changing that some signal on the input side, that I am changing to tweaking that 10 millivolt. Means I am just changing that 1.346 with the 10 millivolt high and 10 millivolt is low. Means peak to peak is 20 millivolt. And on the basis of that, I will check that what is the gain. Okay, so let's try to solve it. Okay, so I am just changing that something here. Okay. So I am just removing this thing and using a sinusoidal signal. Okay, I am superimposing one voltage, that is just a superposition there. That operating point is set, that is VGS. Now I am giving a small signal for that voltage 1.346, your DC voltage. I am superimposing the voltage, that is very small voltage, that is 10 millivolt only. I want to change a 10 millivolt at that point. What is happening at the output side? I am interested on that part. Okay, so I am just giving that. You have a wire. I am just connecting this like this, and you connect it like this. So you have this type of circuit, and now I am changing here. I am going for advance. and I am going for sinusoidal signal. That sinusoidal have a, I am giving the amplitude is 10 millivolt. I want 10 millivolt variation on that 1.346, and that frequency is 5k. Let 5k or 1k, it's up to you. I am just assuming that 5k, that will be easy for understanding. Okay, so I want that, or you can change it 5k or 1k, it's up to you. It's up to you there. Okay, so just I am saying that frequency is 5k. So this is happening here. So this is a representation of sinusoidal input with over the 1.346. 1.346 your DC voltage, and you are adding a 10 millivolt. So in terms of 0.010 you are adding. So basically you are adding 1.356 or 1.326. 336. Okay, so you are changing 10 millivolt high as a peak and 10 millivolt as lower as a peak. So that gate to source voltage is changing here, and I want to figure out what is the V out and V input in terms of output waveform. So I just want to represent that in terms of net. So I am just taking that wire here, and I am assuming this is the wire. Okay, if you want, you can take as a capacitor here also. Why? Because this capacitor will block the DC voltage, and after the DC voltage it will be fluctuate the output. So you can use a DC capacitor also. So you can use a capacitance here. Okay, and you can use that like this. Okay, you can change that value, any value you can take, that is make it 10 micro. It is okay, I think that is 10 micro. You can take any randomly value, and I just give that name, that V in. The input is here, that input signal. If you want, you can change the input signal, and you have a output V out signal. So this is V out. So you have an input, you have an output, and I am just representing like this. So for this type of analysis, you want going for a transient analysis, because you want a input waveform changes of 10 millivolt, and what will happen at the output side. So I am going for transient analysis here. I am not going for DC analysis here. I am going for transient analysis, and they make it for it's 5k. So what is time? So 1 by 5k, it will be 0.2 millisecond. And if you want 5 waveforms, you can take 1 millisecond. Okay, if you want only 2 waveform, 2 period, you can go for 0.4 millisecond. So I am going for 1 millisecond. Okay, so for 1 millisecond, I want to operate that circuit. Okay, and just run it, just save it and run it. So if you run it, it is taking some time, and you know this is an input voltage, 1 period, 2 period, 3 period, 4 period, and 5 period. Of course 5 cycle is going on. Okay, or if you want as much good now, so you can reduce that time, because I want a good picture of that. So you can make that not 0.1 millisecond, make it 0.5 also. So that 0.4, that is okay. So you have only 2 clock in that sinusoidal period. So for 0.4 millisecond, you have that is only 2 cycle, 1 period and second period. So this is 0.4 millisecond or 400 microsecond. So this is your input. This is representation of input. The input is changing that 0 to 10 millivolt to 10. So this is input voltage, that V1 is the voltage V input with respect of ground. But the gate voltage is not V input. The gate voltage is VGS plus V input. So gate voltage is 1.346 plus minus 10 millivolt, because this is 10 sine omega t. So I can say that the VGS is what? That VGS is 1.346 plus 10 sine omega t. Okay. So that is your, basically this is a KVL. You have a two voltage in a series, so you can add it. So that VGS is what? That you can say that overall VGS is what? That is 1.346 plus V1. Okay. And let's talk about what is the output. So I am interested on the output because I want the gain is 10 times of that. So what will be the gain? Just I am checking that V out here. So your input is this. This is your input there, that blue one, that is green one your input and blue one your output. This is representation, this is V out and this is input. And of course it is 180-degree phase difference. Why it is showing the 180-degree phase difference? Because that common source amplifier have a difference of 180-degree. The output is minus GMRD parallel of R0. So the gain is 180-degree phase difference. So if you are interested on that, what will be the gain? So I am just checking that you can take that V out at click here. And you can check it, what is the peak value. That peak value is nearly about 98 point something, and the bottom value is 11101. Yeah, that is something that I am assuming that this is peak to peak is 200 millivolt. So the 200 millivolt upon the input voltage is peak to peak is 10 millivolt upon 10 millivolt plus and 10 millivolt minus. So peak to peak of V out is 200 millivolt and peak to peak of input is 20 millivolt. So 200 millivolt upon 20 millivolt, it is 10. The gain is 10 approximately. By the looking of that waveform, I can say that the gain is approximately 10. How I can say that? You just check it, AV is equal to V out upon V input. The difference of peak to peak V out is 100 millivolt in upside and 100 millivolt at bottom side. So they nearly about 200 millivolt. And the input you are giving a 10 millivolt. So 10 millivolt is rise and 10 millivolt peak on the positive side and 10 millivolt on the bottom side and the negative peak. So that 200 millivolt upon 20 millivolt. So it is providing a 10 times. Okay. Let's figure out what is the exact value of the gain. So this is representing in terms of transient analysis. Now I am going for perfect value. I am interested on the perfect value, just like this. I am perfect. I am trying to find out what is that perfect value. Okay. So for that you are writing that some function that is dot measure and dot measure, and you are writing that gain and parameter, and that is V out by V in. I am just checking it is correct or not. I am just interested to that checking it is correct or not. Said that what is the function. So please wait, I am just checking it. Dot MES measure gain parameter and PARAM and V out by V in. That is correct. That is okay. So you are just writing the SPICE directive. You can take the SPICE directive from the analog lib, not analog lib or just analog lib in a LTspice. You can search it. What is the SPICE directive? What is the directive of that to determine what is the gain? How can you determine? So this is the parameter dot measure gain parameter V out by V in. So you can use this. and you can place it here. Okay, so that measure V out gain parameter V out by V in, and of course this is for value, so I am just giving that this is for value for amplitude. Okay, so this is amplitude for that variation. For that calculation of the gain, I am giving that AC magnitude, and that AC magnitude is approximately 1. I am just assuming that you are giving that AC amplitude is 1 or 10 milli. It is okay, it's up to you, because that gain will be dependent on the AC magnitude. You have two parameters, amplitude and magnitude. So whenever you are giving that amplitude and you are working on a frequency term, that is a transient analysis, and you are giving the AC amplitude, the AC magnitude, well, that will be provided the V out by V input. So I am assuming that AC amplitude is 10 millivolt and press OK. So this is AC is 10 millivolt, and I am trying to determine what is V out. So I am just interested to determine what is the operating point. So on the basis of the operating point, on the basis of the transient only, I can figure out what is happening. So I am just save it and run it. It is taking time. Of course, it is taking time because this is too bulky and my system is also very bulky. That lot of things is having. So okay, I am not interested on the graph. I am just that cancel out this. Okay, and go for view, and you have a spice output log, and the gain is failed. Why the gain is failed there? That gain is failed. Okay. It is okay that you have that parameter is like this. Okay, let's try to write. Why I am going for test? Just cancel out firstly there. Oh, oh, please don't cancel it there. It's draft. That is okay. Yes. Oh, let's try to put it all the values. Dot measure V out, V in, peak to peak, capital V, and this will be V in, and I'm interested on dot measure. Dot MEAS V out, peak to peak, V, and it will be V out. Okay, so I am giving all these values. Okay, so this is this. Everything is okay. Dot measure gain parameter, and this is okay. I am just adding here. Okay, now I am checking what is happening, why it is not showing the gain. So just transient analysis, I am just removing this to transient analysis. This is operating point. Okay, and just save it and run that. I am not interested on that output part. I am interested only view and spice output log. So this is that you have this, and I am just copy it, Control C, and draft, and go for comment text on this Control V, This is your gain there. So that gain is approximately 10 there, 9.9777673. And peak to peak you have a this, and peak to peak is something like this. So the gain is 90. Basically I am interested on the gain only. I am not interested on input, and we know that we input and we out only. So the gain is 9.97. But I want that higher gain. What can I do here? So if you want a higher gain, you can increase that transconductance, or you can increase that RD. Basically gain is dependent on transconductance and RD. So if you want to make that gain is higher, you can increase that what? RD. If I am increasing that RD is 57 to 60 kilo ohm, what will happen? Let's check it. So by the 57 kilo ohm, you find it that this is not providing that higher gain. Let's try to make it 60k or 80k. It's up to you. I am just giving that for that is 60k. Okay, and just save it and run it. And I just want to check that it is increasing now there. I'm interested on this part only. I am not interested on this a lot of things it is there. I am just interested on that gain, and you can make that capital also. There is no meaning that you can write is that gain is like this. Okay, so you can. So that gain is 10.37. Okay, so as you gain increases, as you increase that RD, that 10.37. But you know, we cannot increase as much amount of RD. Why? Because if you increases the RD, your Vout is decreasing, because Vout is VDD minus ID RD. As per RD will increase, your operating point or DC point is going downward. Your MOSFET may be enter in a linear region if Vout is not that much amount. If VDS is not greater than VGS minus VTS, you will face the problem. So you can increase the gain. Okay. So this is the way you can solve it. You can take one assignment. There's design of a common source amplifier with a resistive load. The gain is 15. That is make it gain. The magnitude is 15. Okay. That is V out by V in is 15. 15 or more than 15. That is okay. Okay. So I am designing for 20 dB. You will design for 30 or 35 dB. Okay. So design it, that logic in such a way कि what is RD, what is the VGS, and how can you find it. And you know that resistance is a problem. So how can you avoid it? You can just replace this resistance and use a MOSFET. And if you use a MOSFET, that MOSFET, if lambda is not that much effective, you will find higher resistance. So this 16K is very, very tough to fabricate in terms of layout. So you can use a PMOS, or you can use a bias as an NMOS. Okay, so this is the way. Please work on it so that you can analyze, you can relate the theory, in terms of tool designing or circuit designing in terms of like this. Okay, and for that, of course, this for 60K, this is not valid. For the DC, for this 60K, this value is changed. You can check it also. So you can go for operating point, and for this 60K, that value is changed there. So you can check it, that this is the value there. Okay. So now current is same, VGS is 1.3, but the VDS is not. VDS was In previously it was, I think, is 3.27. Now it is 3.20. Why? Because if you are increasing the resistance, V out is decreasing with that. So now the VDS is decreases from 3.27 to 3.20. So please work on it and design it, okay? And that will be give you an interest. How can you design a common source amplifier? So tomorrow we will design a common source amplifier with a resistive layout on cadence. This is LTspice. Here you can set that VT naught. But once you go for the technology node, if you have a GPDK and you have a TSMC and you have a GF, Global Foundry or UMC or any type of technology node you have, so that you have a technology node, on the basis of the technology node you have a VTH. So firstly calculate it, what is that VTH you have, and on the basis of that you will define that calculation. So tomorrow we will design a common source amplifier with that with the cadence virtuoso. So for now, thank you so much everyone. Please work on it and we will continue like this only. Okay. So thank you so much dear.